Hi, my name is Ryan Thompson, and this is my final exam, question 5 for CPSC 5210. In question 5, we're asked to evaluate, we have a few different subsections, each dealing with the Van Imboden Boas tree. In 5A, you're asked to talk about the time complexity of this tree. We're asked to talk about what is the worst case for the Boas tree, and also how is it different than other worst case trees. Well, the worst case here is big O, log U, if possible values. A Van Imboden tree creates a discrete spot for every value 0 to n. That's why this isn't log n, this is log U, because spots that will be empty if a value is not there, but it will go all the way from 0 to n. Typically, other algorithms' performance on an operation is measured only on the number of elements that they're evaluating. So the performance, if n is 10, it's over log n, or n log n, or 10 log base 2, 10. Here, if u is 10, or if there's 10 elements, but the last element is, the maximum element is 100, you would have 100 units, so it'd be log 100. So this illustrates that even if there are gaps between an element, a standard algorithm with the same number n will have the same time complexity, whereas a Van Imboden tree will not. So this is a plus and it's a minus, because if you have large gaps between the numbers of n, you'll have a bunch of empty spots on the Boas tree, which could result in a memory issue potentially. But also, the Boas tree can handle very large numbers or a lot of elements because of its unique structure and its unique way to index into an element's key value. Another important note is that if an element is inserted into a standard algorithm and is less than the maximum, it will increase the time complexity since n has increased. But a Van Imboden tree will have already made a placeholder for that missing value, since no duplicates are allowed, and the time complexity will remain the same. So what does that exactly mean? That say in an array that you have to do an operation on or create a tree for, n is 100. The maximum value of n is 100, so 100 represents the maximum key. Well, the Boas tree will create a placeholder for every value 0 to 100 with no duplicates. So if n is only 10, the Boas tree will have 90 other gaps, and another tree may not. But when you have to insert a new value, say now, or you have to insert a new value, so n goes from 10 to 11, this adds to the time complexity of the previous or the other standard algorithms, but not for the Boas tree, as long as the new number added is less than the maximum key that already exists. Because it's already got these spots created, it's simply an insertion. There's no more sorting to go on. There's no other procedures that have to keep a binary or a red-black tree that have to maintain these structures. The placeholder is already there. So the Boas tree is very good for these large numbers where you have an extreme range of values that can be added or removed at whim without having to really change the configuration of the network. The second question, we're supposed to describe the high X and low X in terms of this tree structure. So high X indicates what cluster that X is in, because that's the way the Boas tree is broken down. So high X is equal to the floor of X divided by square root of U. in terms of the index of x, it gives the most significant LU, or log U divided by 2 bits of x. So it's going to give the front part of x. And it's going to tell you which of these basic clusters it should fall into. Low x indicates the position of x in that cluster. So once you identify what cluster it should fall into with high x, you need to know which part of that it falls into. So low x is equal to x mod square root u. In terms of the index of x, gives the least significant log u divided by 2 bits of x. So these seem like two very disconnected parts, but together x is equal to index high and low. So the high x tells you which cluster it falls into, the most significant part, and the low x will tell you which part of that cluster it falls into. So it could be some of these clusters that we'll see only have 2 bits of information. The low x will tell you if it falls into the first bit or the second bit of that cluster. So that is the high x and low x's function in the Boas tree, is to help quickly index a key value to which cluster and then which part of that cluster, which position in that cluster x falls into. In C here, you're asked to modify the Boas tree structure to include 13. Well, when you look at that diagram, only cluster 3 changes because there's already a placeholder for 12, 13, and some other empty values. So it's not breaching the maximum, which was 15. So here you can see my example of how this new cluster works. So we've already identified that it should be in cluster 3 because of high x's ability here. Now we need to update x because update cluster 3 because previously it does not exist, or it's 0, 0. So it does exist because you already have that placeholder, but the values represented are 0. Now, using low x and plugging 13 in, you wind up that it belongs in the second position. So here, originally it's 0. Now we flip it to 1. And in the summary value, A being 1 already was true, or it was 0. And now, no, yes, A was 0. And now because it has at least one element, it goes to 1. And this was already 1 because 14 and 15 already existed. So we had to update the 0, the second bit of information, from A in the cluster of which part of the cluster it fell into. And then we had to update the summary as well. And again, this part of the cluster, the first part, falls into, or it was value 13 that we're adding, so it falls into the third cluster, the first section here, and 1. So that's all that really needs to be updated, and that highlights the benefits of this Boas tree, that this was a very fast insertion problem just to perform this high x, low x calculation, but you didn't change the time complexity at all for any operation. So it remained at big O log u.